This is XPO-PID. It is useful in electrical lab and control system lab. This is master unit. This master unit consisting of power supply, analog meters, digital DPMs on top board and computer interface panel in left side. This is analog PID to control the process and function generator for the set point. This is total master unit. This is PID top board. Here this is 17 volt unregulated power supply, 0 to 17 volt. This is 7 to 14 volt DC variable, 3 ampere. This is ground. This is minus 12 volt fix and this is plus 12 volt fix. This is analog meters. This is DC voltmeter, plus 10, 0, plus 10, minus 10. This is DC voltmeter, 0 to 2.5 volt. This is DPMs. Left side DPM is useful for measurement of speed and voltage. In left side it is speed and right side it is measuring voltage. This is right side DPM is useful for measure the temperature and intensity. Left side is for temperature, right side is for intensity. This is top board of XPO-PID. This is 7 to 14 volt DC, 3 ampere, useful for stepper motor process. This is 17 volt unregulated, useful for process 1 and process 2. This is fixed power supply, 0, minus 12, plus 12, 500 milliampere. These are analog meters. This is DC voltmeter, minus 10, plus 10. This is DC voltmeter, 0 to 2.5 volt. This is DPM, left side to measure the speed and right side voltage. This is DPM, 4-digit DPM. This is 4-digit DPM to measure the temperature, intensity. This is 2-pole, 2-way switch, left side for selecting temperature and right side to select the intensity. Temperature shows in degree centigrade, intensity shows in lux. This is sync output, useful in process 1, process 2. This is computer interface adapter, useful to monitor various graphs of the processes. This is power on LED. This is analog simulation signal, 0 to 2.5 volt DC for testing purpose. These are 4 channels, analog input channels, channel 0, channel 1, channel 2, channel 3. You can monitor maximum voltage 0 to 2.5 volt on these channels. This is DAC output. You can select the range 0 to 2.5 volt or 12 volt, and this is ground. This block is V to I converter. Input voltage of V to I converter is 0 to 2.5 volt. Output current is 4 to 20 milliampere or 0 to 20 milliampere in downward switch condition. This is V2 PWM converter. Input voltage 0 to 2.5 volt. Output is 1 kilohertz plus or minus 9 volt output. This is analog PID. It operates on plus 9 minus 9 volt op-amp based analog PID card. Here it is the controller output is A1. This is analog PID which is operating on plus 9 minus 9 voltage. This is A1 is controller output, and these three potentiometers are, this is PB. You can select the percentage of PB in proportional mode. Integral mode, you can select the integral mode in the with this potentiometer, and this is the third potentiometer. Select the D action. These two switches, 2-pole 2 switches, are useful for slow mode and fast mode. Slow mode for the PC and fast mode is selecting for DSO or analog CRO. These two switches are, if you select it, I action will be started, select and deselect, and this is D action, select and deselect mode. Left side are deselect mode and right side is select mode. This potentiometer is set point minus 9 to plus 9. You can set the set point. This is set point. Output will be A11. You can monitor vary the voltage plus 9 to minus 9 on set point output. These are level shifters. Mainly level shifter useful. This PID card is operated at minus 9 plus 9, but our computer interface card is run on 0 to 2.5 volt. So hence, to reduce the voltage, here we use level shifters. This is one level shifter. A13 is input minus 9 to plus 9 voltage. A14 is output 0 to 2.5 volt. This is also one level shifter. A15 minus 9 to plus 9 voltage. Output is 0 to 2.5 voltage. This is function generator. Point 0.1 Hz to 166 Hz. This is selecting square wave, sine wave and triangular wave. Extreme bottom side is square wave, extreme top position is triangular wave, and middle is sine wave. And there is a ranges, you can select range 1 and range 2. Normally using PC, range 1 is needed, and this is for selection of slow and fast. Slow mode is for the PC and fast mode is for CRO. Always for the PC, slow mode and select range 1 and select square wave by default. Function generator output is at A17, output voltage minus 9 plus 9 volt. For the function generator, these are two potentiometers. One is for amplitude variation and bottom side potentiometer, and this potentiometer is useful for frequency variation. Insert CD on CD drive, double click at PID 10.9, double click at PID setup 10.9. So your PID installation is starts. Click at next, click at next, click at next, next. You are up to finish. You get on program files PID 10.9. click at 10.9. This is window of panel. Here you can select integral time, sampling time, derivative gain, set value, and proportional band, and derivative time. And the other mode is graph mode. This is graph mode. You can see the graphs in graph mode. This is process simulator experimental panel. Useful for first order, second order, and third order. In this panel, here these are three blocks are lag integration block, identical blocks. Input is at 4 and 5 BS5, output is 6 and 7. Left side toggle 2-pole 2-way switch, top position is lag and bottom side is integral. Right side 2-pole 2-way switch, useful for PC, selecting PC or DSO. Normally in PC select at slow mode. This also same lag integration block. This is also same block for lag integration. Here it is plus 12 volt and minus 12 volt ground. This power supply needed. This is transport lag. Input is 8-9, output is 10-11. Slow and fast mode. Normally in PC it should be needed at slow position. And this is lead lag compensator, and this is lead compensator. This is lag compensator. All switches should be at slow position for the PC and fast position for the CR. These two are level shifters. Left side level shifter is 2.5 volt to -9 +9. Right side level shifter is -9 to +9 to 2.5 volt. These are summer 1, summer 2. These are disturbances. You can create disturbance in process by this adding disturbances. To select the gain, you can using potentiometer you can select the gain in the process. This is overall process simulator experimental panel CE1. This is example of one experiment: proportional integration derivative with step-in change, first order lag with transport lag. For this experiment, connect CIA card at USB at computer interface adapter. Connect other end of the USB cable. In USB port using patch cord. Connect ground connect plus 12 volt connect -12 volt. We are doing experiment using digital PID, hence DAC output to level shifter and level shifter output to input of transport lag and output of the transport lag 10 to 16, input of lag, and from 18 output of the lag 32. 32 is the inverter. Connect 33 to A13, input of level shifter. A14 output of level shifter connected to channel 1. And connect FG output A15, input of level shifter, output of level shifter to channel 1. Connect ground to 49 to A12. Connect 48 ground to ground of computer interfacing card. Select the switches at slow mode and lag position, and function generator switches also at slow mode and position 1, and select square wave to show good response. Go to computer. After connecting patch cords, go to PC, double click at PID. So you will get window of panel, main PID panel. Select settings. After double click, settings will come. Here select parallel port and select USB mode, and select channel for measure variable channel 0, and set value is channel 1, and ratio factor is 1, minimum is 0, maximum is 100, and select OK. Set values: integral time 64000, sampling time 0.1, derivation time 0, proportional band 100, and select at auto start. Click at auto start, save. Yes, go click at graph. You will see the graph on your PC with proportional band 100 in proportional mode. Black is set value, red is measured value. This is P action, and you can change I action, introduce I action in go to panel and set integral time 3.5 and go to graph. In this case, adding integration, so error will be reduced, but however some error is there. to reduce minimize error, add D action. .5 and proportional band is 100. You can reduce error. To see proportional integration derivation with minimized error using digital PID, this is output of the graph on page number 3-103, third chapter, page number 103. Same will be observed on your PC screen with PB 140%, TI 1 second, TD 0.2 on panel. Time 1, derivation time is 0.2, PB is 100, and this is graph. This is DC motor position control trainer process 3. Connect 15 pin cable here, and other side connect servo interface panel. This is measured variable servo port from 0 to 360 degree. This is set point using linear port 0 to 270 degree. These are two DC motors connected, coupling with coupler to generate the voltage. One is act as a motor, other is acting as a generator. To run the DC motor, position control of DC motor using set point change. For this experiment, connect patch cords plus 12 volt to plus 12, minus 12 to minus 12, ground to ground. Servo amplifier input of servo interface panel connect to controller output of A1. Set point of servo interface panel of 6th number tag to A9 set point change, and connect patch cord measured value of servo interface panel to A10 of analog PID card. Always set point port at 0 position, and PB should be 5% and kept at slow mode. Deselect I, TI and TD and power on by PID and power on DC position trainer. Here you can observe LED, power on LED on DC motion trainer. Here you can observe, you can change the set point. This is set point. You can change the set point. The measure will follow according to your set point. Suppose if you change the set point by 180 degree, so measure value will be followed by set point. If you change the set point 270 degree, measure value is follow the set point. If it is 360 degree, it is 360 degree. If you want set point at 90 degree, it is also 90 degree. So here we perform the experiment using DC motion trainer using analog PID in standalone mode. We are doing patch cords, connecting patch cords of position control using DC motor process. For that, connect plus 12, minus 12 to minus 12, ground to ground. Then connect 4 to A1, connect 7 to A15, A16 to channel 0. Connect 7 to A10 and A10 to A15, A16 to channel 0. Then connect A11 to A13 for set point and A14 to channel 1, A12 to 35. FG square wave A17 to A9. Power on DC motion control. Connect set function generator. Here, according to your function generator input, motor will rotate. Go to PID 10, click at PID 10.9, graph. Here you go to process monitor mode because you are doing experiment using analog PID. So hence select channel 0, channel 1 and select graph plot. Here black line is set point, red line is measured variable. Here you observe the waveform, there is a error of 50%. To reduce error, connect proportional band, reduce proportional band by 25%. Error will be reduced. Further reducing error, select I DC motor is fast process. To introduce I, oscillations will come. Here we are doing closed loop control with digital PID using speed experiment. Previously we have studied position experiment. Here we are going to study speed of the motor. Connect patch cords +12 to +12, -12 to -12, ground to ground. Here connect DAC output to level shifter. DAC output from 5 of computer interface panel to 31 level shifter input of the CE3 panel. This is because we are doing experiment of digital PID, hence DAC output has to be connected to 31 and level shifter output has to be connected to servo interface panel of 4 number tag of the CE3. Connect tacho output of the 11 number tag of the CE3 to channel 0, channel 1 connected to level shifter of A14 and function generator output has to be connected to input of the level shifter A13. Power on PID and power on DC motion control trainer process 3 and here PID controller trainer setting, set value is channel 1, measured value is channel 0, parallel port is select USB, minimum value 0, maximum value 100 and OK. Here integral time is 64000 because we are doing experiment of P action, so no integration time. Always sampling time 0.1 due to it is a very fast process. Auto start, save, yes and graph. Final waveform of the position control using digital PID, speed control of digital PID using DC motor process.